Welcome to the course module of Communication System Engineering. And in this video, we are going to learn about energy spectral density function and power spectral density function. So let's begin this discussion. So normally when we discuss about the noise calculation or noise signal to noise ratio calculation in communication systems, then we normally talk about the energy spectral density function and power spectral density function. So these two words are normally we come across. So we have to understand what is energy spectral density function and power spectral density function. So let's try to see this, what is energy and power for a deterministic signal that we have already discussed in my previous video. So what is deterministic signal? I have already explained, but here I would like to mention that the deterministic signals are those signals whose mathematical form is normally known and it can be determined. Okay, its future values we can determine because it is having a known graphical method, known graphical form, or it has its known mathematical form. So if we have any mathematical expression, we can substitute for any time, and then we will be able to determine its futuristic values. And therefore, it is referred as the deterministic signals. And you know that, for example, if we write any exponential function over the time, or if we write any sinusoidal function over the time, those all signals are deterministic in nature. I also have already discussed about the what is energy signal and power signal. So here we can see that normally in the case of energy signals, normally energy signals can have the finite duration, and therefore it is normally having the finite energy. Okay, and therefore we can calculate its energy by following this particular formula. Okay, let us say that if we have any time domain waveform which is denoted by gt, and if it is a complex signal, obviously we have to take this mod and then we have to square it, and then we have to integrate it over the time minus infinity to infinity. So normally we have to take that duration of the time in which the signal exists, because it is not necessary, because it is energy signal, so it should not be varying from minus infinity to infinity, right? So whatever the existing period for this particular GT, that we have to substitute as a limit. Okay. So normally, if it is not a complex signal, that time you can remove this mod sign. Okay, we can directly write it as g square t. Okay, g square t, and then we can do this integration over the time. Similarly, if we talk about the power signal, right? So normally in the power signal, such signals would be having its infinite duration. And therefore, when we calculate the energy, that time this energy will not be finite. Okay, it is going to be infinite when we do the integration from minus infinity to infinity. And therefore, we talk about the power of the signal, right? So to calculate the power of the signal, generally we are following this particular formula I have already explained in my previous lectures. Okay, so limit t tends to infinity 1 by t, and then we have to integrate over a particular interval of time. Okay, so this way we can calculate the power. So this is the known relationship, known mathematical form that I have already discussed in my previous lectures about the energy signal and the power signal. So let's try to see if suppose I will be just using another theorem, okay, directly this property of the Parsifal's theorem. So suppose that if we have this time domain, any signal which is represented by gt, and if its Fourier transform is also known to be gf. Okay, so normally Parseval's theorem says that if its Fourier transform is known, then we can directly calculate its energy. Okay, so that formula you can say it is E equals to minus infinity to infinity again. This will be mod gf whole square df. Okay, so this way, if you know this Fourier transform or its time domain expressions, right? So either you can use this particular formula in which we are having the time domain expression. Here you can see it is gt, or if you have its Fourier transform, again you can use this particular formula by using the Parseval's theorem, right? So here I had just given this proof of Parseval's theorem, how this EG can be actually evaluated, right? So here you can see, those who are interested, here you can see it is EG actually, if this particular expression I have derived for the complex signal, but it is also valid for the real signals. Okay, so let us say if we are talking about any signal which is GT, a complex signal, then obviously its energy will be given by minus infinity to infinity gt and complex conjugate of gt dt. Okay, and then we have to integrate it over this minus infinity to infinity, right? Then here you can just see that I have just replaced this g star t with its equivalent Fourier transform, right? So here I have just written the Fourier transform expression here, okay? And then just some of the manipulation we have performed here, you can see, because this integration is both are having this limit from minus infinity to infinity. Here again, it is minus infinity to infinity. And we are having a certain function of frequency and certain function of time, okay? And this integration is actually being done with respect to df, and here it is with respect to dt. So we can just change this terms and then interchange these terms, and then we can rewrite this expression in this form, okay? G star f, then minus infinity to infinity gt e to the power minus j2 pi f t dt, and then df, right? So this way I can rewrite this expression, and then finally you can see this expression is corresponding to gf, right? This expression is corresponding to gf. It is corresponding to it is the definition of your Fourier transform, and then you can rewrite this expression as gf. So ultimately, this expression will be getting e equals to minus infinity to infinity, and then mod of gf whole square df. So this is the actual result that we have to utilize, right, for calculating the energy. So normally, suppose if any signals, right, any signal, if it is deterministic signal normally, or if it is even random signals, right? So I will be discussing about the random signal in the next slide. So here you can just see, let us suppose if we have any signal gt, okay, whose Fourier transform gf is known. Normally, if it is passed through any filter whose frequency response is given by hf, in that cases, normally we can calculate what will be the energy of this output, okay? So let us say this output yt is this, the output of this particular filter is yt, and its Fourier transform is to be yf. So as we know that this yt can be calculated by convoluting this input signal with the impulse response of this particular filter. So normally yt will be equals to gt convolve with ht, and obviously if you take the Fourier transform both the sides, then you will be getting this yf equal to gf multiplied with the hf, right? So hf is the frequency response of this particular filter. So if you substitute, if you use this Parsifal's identity, we can calculate this output energy ey. So this output energy ey you can calculate, that will be coming out as minus infinity to infinity mod of yf whole square df, okay? So here you can substitute it for gf into hf whole square and df, right? So just I'm substituting this value. So this way actually we can calculate the output energy, okay? Output energy if you pass any signal gt through such filters. Now just try to understand, suppose that if we interested in calculating the energy and power for a random process, okay? So normally I have already explained number of times what is random process, okay? In communication we come across the noise process normally, and normally this noise is not a deterministic signals, because it's mathematical known, mathematical expressions are not known, okay? And therefore we cannot determine at what instant of time this noise, what value it can take, and therefore it is referred as the random process, okay? So random process is normally a time function. It is the random variable which is a function of time, right? So here I can just denote it you like suppose that we are having a random process and it is having different sample functions, okay? So here I can show you that here, suppose that this is one of the sample function of a random process, capital xt. So let us say this is the capital xt that we have denoted, okay, as a random process. And within this random process, we are having a different sample functions, okay? So this is the first sample function, then this is another sample function, okay? This is another sample function, here you can see. Then again, we are having this another sample function. So all these sample functions are actually random in nature with respect to time. So I have already explained number of times. Suppose if we are interested in knowing the temperature of a particular city in a particular time, okay, let us say in between 12 p.m. to 3 p.m. if we are interested, then we can get the complete graph between 12 p.m. to 3 p.m. We can measure and we can record these values, okay, over the time. Similarly, because this record that we are making, or the measurement that we are making between 12 to 3 p.m., it can be done on a specific day, or we can also make a measurement for a month, okay, for a year, or for a 20 years, like that. Okay, so we can get a huge number of sample functions. So accordingly, here we can consider that this is the time function. This is omega 1, means it is the day one measurement. Okay, you can consider that this sample function is corresponding to the day one measurement. Similarly, this is for day two measurement. Similarly, this one is for a day three measurement. Okay, so this way you can understand. So in a similar fashion, the way we have calculated the energy for deterministic signals, again we can calculate this energy for the random process also. Okay, so here it is epsilon I, and again, just we have to substitute for this particular random samples, right? So you remember that we have to substitute for the random functions, right? So we have to substitute for a random function. So sample function, sorry. So it is a sample function has to be substituted, right? So here you can see, because we have to substitute for the I. So if you I equals to 1, then for this particular graph, okay, only one graph that we have considered here. For this particular sample function, we are going to calculate what will be the energy for a particular time period that we have to calculate. Okay, similarly, we can calculate the power also for a particular sample function, right? So once you are calculating all this for a particular sample function, you know that when you change this sample function, okay, when omega I is omega 1, if it is omega 2, if it is omega 3, the sample function will change. And therefore, we know that this energy values, whatever we are going to get, it will be a different value depending on the sample functions taken for calculating the energy, right? And therefore, we can say that this energy values, whatever we are calculating for a random process, okay, for this particular random process xt, which is having a huge number of sample functions, okay, this will be a random variable. Okay, this will be a random variable because it is going to take a random values, right? So therefore, normally when we talk about the energy and the power of a random process, we do follow this particular formula, but we are actually interested in what will be the average value of this particular energy or power. Okay, we are interested in the average values, right? So therefore, what we can do is we can denote all these outcomes. Okay, this epsilon I, this all outcomes will be actually denoted by a random variable epsilon x. Similarly, all this energy, this power values will be outcome of the power values for each random each sample function will be denoted by pi. Okay, so this outcomes will be denoted as random variable px, right? So here we have to calculate what will be the energy, what will be the average value or expected value of this energies or powers, right? So that can be here calculated like expected value of epsilon x and the expected value of your this power, right, of all the sample functions, right? What will be the average values? So that average value you can calculate again. So it is just expected value we have to substitute, and then we are actually following this particular formula. Minus infinity to infinity, it is a random process x square t dt, right? And then again, this, if you substitute for minus infinity to infinity, if you calculate this expected value, okay, because here epsilon x is equals to this particular expression. Okay, if you calculate the expected value, this expected value will be coming out to be as a autocorrelation function, right? So what is autocorrelation function? I will be explaining you the next slide. So don't bother about it, what is autocorrelation function. So, but you have to remember that this way we have to calculate the expected value or average value of the energy for this particular random process. Similarly, we have to calculate what will be the average value. Okay, so you first remember that we have to calculate the power or energy for a particular sample function, and then we have to average it out, okay, for all the sample functions available, right? We have to take all these energy values and then we have to average it out so that we will be getting the average value. So this way we are actually calculating the average value, and normally this average value will be related with the autocorrelation function, right? So now we have already discussed this, what will be the energy and the power, okay, of a deterministic signal of a random or a random process. Then here we have to understand what is the energy spectral density function. So normally energy spectral density function, as I written here in the bracket, that it is the energy per unit bandwidth in hertz, right? What is the energy per unit bandwidth in hertz? So let's try to understand what we have already written for the deterministic case. The same thing will be also applied for the non-deterministic case, okay, for the random process. So if we have any known signal or if unknown signal, maybe it may be a random process. If its Fourier transform is GF, if it is passed through the filter, then we will be going to get the output equals to YT. And then corresponding Fourier transform will be YF. And we know that what will be the energy EY. This energy EY will be equals to minus infinity to infinity mod of GF HF whole square and DF, right? So because there is a symmetry in the Fourier transform, normally we can rewrite this expression in the form of EY equals to twice of 0 to infinity and mod of GF HF whole square DF. So this integration limit will vary from for which this particular product will exist, okay? So when this product will coexist for a certain range of frequencies, that particular frequency range we have to consider for your integration process. So here you can see, suppose that this filter HFs that I have shown here. So let us try to understand if this filter is a very narrow band pass filter. Okay, let us say it is a very narrow band pass filter of having this type of characteristics, let us say, right? Normally, if in this case, you can see that this band pass filter is having a central frequency at f naught, and it is having a certain bandwidth, which is denoted as delta f, okay? This value of HF in the pass band is equals to 1. Otherwise, this value is 0. So normally, if any Fourier transform, let us say we are having any Fourier transform of GF, if this is going to be multiplied with the HF, we know that only this much of portion is going to be survived, okay? Because HF is not available or it is 0 for other range of frequencies, right? That is just available for F naught, which is centered at F equals to F naught and having its width equals to delta F. So only for this much of width of your frequency, the GF is going to be survived, okay? Or it is going to be giving you certain product other than the 0. Otherwise, at all other places, because HF is 0, the product with the GF is going to be 0. So that you have to remember, right? So here we can see this if HF equals to 1, and if you wish to calculate what will be the energy of this YT signal, we can follow this identity, right? 2 into 0 to infinity mod of GF whole square. Here I have substituted HF equals to 1. So let us say that this delta F is very small value, right? Very small. Delta F tends to be 0. So in that case, I can substitute this F equals to be GF, directly F naught, okay? So here you can see this value is twice of mod of GF F naught mod square, okay? So 2 into mod GF naught whole square, right? Into DF. Right, so this way we can calculate the total energy. So DF means it is delta F that we have to multiply. So if you able to calculate this value, you will be able to calculate what will be the energy, because it is a very narrow band filter. Otherwise, you can substitute for this limit, right? So normally, if you get this GF naught, you will be able to calculate what will be the EY, okay? And you have to also multiply this small df, right? So this way, here we can see that normally, because if you choose this delta f to be equals to 1 hertz, in that case, what I can say that this GF naught, okay, mod of GF naught, this particular function, mod of GF naught whole square is actually denoting you what will be the energy content available in per unit bandwidth in hertz, right? Because it is showing you certain energy value, and then we are actually multiplying with the width of this particular pass band, right? So if you multiply these two things together, you will be able to get the total energy value, because we are considering this delta f is almost equals to 1 hertz. In that case, if you multiply this particular value, then you will be getting what will be the total energy, okay, that we are going to get. So normally this particular function, mathematically, it is defined as the energy spectral density. So what does it mean by energy spectral density? What is the energy available per unit hertz, okay, per unit bandwidth in hertz, or you can say energy per unit hertz. So that will be your energy spectral density, and it is denoted by psi gf, which is equals to mod of gf whole square. And therefore, if you wish to represent into this energy spectral density, then the power can be represented as Eg equals to minus infinity to infinity psi gf df. Okay, it means that if you know this psi gf, right? If you know this energy spectral density function, then if you integrate it over a certain range in which this product is going to coexist, okay, that time you will be able to calculate what will be the total energy. Okay, so this simple formula, you have to remember this particular formula you have to give. Okay, so here you can see that we have actually done this multiplication after considering hf equals to 1, and here we are going to get this gf, okay, mod of gf whole square. So this is the mod of gf whole square, and here you can see that this particular value of at f naught, we are going to get this mod of gf whole square, right? Gf naught whole square. So this way you have to calculate the total energy. Similarly, as we have defined the energy spectral density function, similarly we can also define the this power spectral density function, right? So before that, here you can see this, if suppose that, as I have already explained you, if we know the Fourier transform of any mathematical expressions, time domain mathematical expression, if we know the Fourier transform, then we can calculate the Fourier transform of its output, okay? And then actually we can directly calculate the EY by noting this particular formula, right? EY equals to 2 into 0 to the power 0 to infinity and mod gf hf whole square d. Similarly, if instead of knowing the Fourier transform, if you know the power spectral density function, let us say, okay, so suppose that we are having any input signal xt, okay, and if we know its power spectral density, which is xf, and then if this particular signal is passed through a filter hf, then let us say this is the yt, okay, this is the output signal, and let us say this yf denotes the its Fourier transform of yt. So here you try to understand this xf is actually denoting the Fourier transform of xt, and we have to show that what will be the relation between the energy spectral density of output to the input. Okay, so how to calculate this yf? We know that yf will be xf multiplied with the hf. So remember that this xf is actually its Fourier transform of the xt. It is not power spectral, it is not the energy spectral density function. So yf will be equals to xf multiplied with the hf. Okay, so here you can just take the mod and then you can square it. So this way you can read this expression mod of yf whole square equals to mod of hf whole square, hf mod of hf whole square. So normally this mod of xf whole square will be giving you the energy spectral density function of the input, right? So of this input process, this will be giving you input ESD, right? Input energy spectral density function. So normally this mod of yf whole square will be giving you the energy spectral density function of the output, right? So this output energy spectral density function will be equals to input energy spectral density function multiplied with the mod of hf whole square. So this is very important relationship. So even if you know the input ESD, right, energy spectral density function, then you can directly calculate the output energy spectral density function by following this particular formula, psi yf equals to psi xf multiplied with the mod of hf whole square. So now you try to understand what is power and power spectral density function. Okay, so power, as I have already explained you in the previous slide about the deterministic signal. So let us say that if we are having any signal which is a power signal, right? So here you can see, let us say this is our power signal, any power signal, right? Then obviously this power will be defined as Pg equals to limit t tends to infinity 1 upon t integration over minus t by 2 to t by 2 ga square dt. So this way we can define this power. Okay, you remember that all these energies and powers are the normalized energy, energy and powers. Okay, I have already explained number of times. It is calculated with respect to load value equals to 1 ohm, right? So here I have just redefined this signal, right? So I have just taken the truncated version of this GT, okay, a truncated version, because this particular GT is defined over the infinite duration, and because it is having infinite energy. So what I am trying to say is that, let us say if we define a truncated version of the signal, which is defined by GTT. So here you can see that this GTT is equals to GT for this time range. Okay, this from minus T by 2 to capital T by 2. It is the same signal that we have defined, and otherwise the signal is 0. So once we have truncated this signal, this power signal will become the energy signal, and therefore we can calculate what will be the energy of this EGT, right? So this truncated version of the signal will have this particular energy. EGT equals to minus infinity to infinity G square T T dt, right? So this way we can define the energy of the signal. So normally here you can see that this portion, okay, if you see this particular portion, if you see basically if you try to define this particular G square T, and if you consider that this GT is actually made up of this GTT, okay, it is just the repetition of this particular truncated signal. In that case, we can redefine this particular interval for EGT will be from minus T by T to capital T by 2, okay. So this particular integration will be giving you this value. You see this, okay, this particular portion, right? So this particular portion will be giving you this particular EGT value, okay? So here I can rewrite this particular expression of the power of this GT signal, right? So this expression PG will be equal to limit T tends to infinity. It is EGT upon T, okay, capital T, where T tends to infinity. Because we are considering that this truncated version, if we repeat this truncated version of this signal over the infinite range, we will be able to reconstruct this GT signal. So therefore, this PG is actually given as limit T tends to infinity EGT upon T. So here you can understand that basically if you see this power is nothing but the time average of your energy signal, okay, time average of your energy. So once you will be able to calculate the energy value of your energy signal, then obviously you will be, if you time average this energy over an infinite range, then you will be able to calculate the power. So as we know that the power is also defined as the energy per unit time. So here it is actually you are getting as the time average of your energies, right? So or otherwise you can also say that it is the mean of its square value, because it is, we are squaring the signal, right, to get this energy value. So that's why we are saying that we are calculating the mean, because we are calculating this value over the 1 upon T. So we are calculating the time average of this square value, right? So this is where PG equals to limit T tends to infinity EGT upon T. So again, we can use the Parsifal's theorem, right? So if we have this EGT equals to minus infinity to infinity J square T T df dt. Sorry, just you make this correction. It should be dt. Okay, it is not df. Okay. Then if you have the Fourier transform of this GTT, then you can directly substitute for a Fourier transform here, and then you can square it and you can integrate over the frequency range. So this way you can rewrite this particular expression. So here this PG can be redefined. It will be limit T tends to infinity 1 upon T. And here you can write minus infinity to infinity mod of GTF square DF. So I'm just interchanging, I'm just taking this limit inside this particular integration. Okay, so minus infinity to infinity limit T tends to infinity. This value will be mod of GTF whole square upon TDF. And altogether this term, okay, with limit T tends to infinity and mod of GTF whole square by T is mathematically defined as the power spectral density function, right? So this is actually defined as the power spectral density function, SGF. Mathematically, it is SGF equals to limit T tends to infinity, a mod of GTF whole square upon T. So this way we have actually defined the power spectral density function. As I said that the energy spectral density function actually tells you that how this energy is actually distributed among different frequency component, or you can say that energy per unit hertz. Similarly, here the power also denotes you what will be the power means in watts per unit hertz. Okay, so that will be the actual meaning of the power spectral density. So if you know the power per unit hertz distribution, then if you do the integration over the entire range of frequencies, okay, then you will be able to calculate the total power. So this total power will be twice, as we know that, because again it will be a symmetrical function of frequency. You can rewrite this expression PG equals to this PG is the total power, you remember. Okay, we are calculating the total power of this signal xt. So this pg will be equals to twice of 0 to infinity as gf and df. So remember that we have to substitute for that particular frequency range over which this SGF will exist. Okay, remember that. So this way we can calculate the power, okay, of any signal. Now you consider if we, as we said that we are actually calculating this power, okay. So this power is actually, we can, power spectral density is actually also having certain relation with the time autocorrelation function, okay. So here we have to see how this time autocorrelation function of the deterministic signals can be defined. So here you can see, suppose that we are having any real energy signal, let us say, okay, if we have any real signal, real energy signal, that time the mathematical definition of the time autocorrelation function of a deterministic signal is actually is this, okay, psi g tau, okay. So here we define minus infinity to infinity gt multiplied with the gt plus minus tau, okay. It can be either take plus sign or it may be a minus sign, and then we have to multiply it together, and then we have to integrate over the time, okay. So this way actually we have to calculate the time autocorrelation of a deterministic signal. So here you can see, let us say that this is our deterministic signal gt, let us say this is our signal, this is our waveform, okay. So if we wish to calculate the time autocorrelation, so normally the time autocorrelation show you what is the means it is actually the measuring the randomness into the signal, right? So whether it is a highly a highly random signal or it is less random signal, that it will be shown by the time autocorrelation function. So basically it is the measurement of randomness of any particular signal. So here you can see how to calculate this signal. If it is gt, you can if you substitute gt minus tau, that time this signal will be this gt minus tau will be shifted right side, and then it is getting multiplied. So here you can see that these two signals, okay. If we multiply this gt minus tau, okay, so here you can see this dotted curve because it is right shifted by a time amount, tau amount, okay. So tau seconds. So normally here you can see, because it is right shifted, this overlap portion is going to give you a certain product, okay. This is the overlap portion. So this is your actual gt, this curve, this solid curve here you can say this, okay. This is your actual gt, and this dashed curve here you can see that it is the right shifted version of your gt, right? So whatever be the overlap portion between these two, it is going to give you a certain product value, right? And for other values where it is there is no coexist, these two signals are not coexist, there the product is going to be zero. So normally we have to calculate for a different amount of tau. So normally tau, when it is equals to 0, that time this overlap will be maximum, okay. Whenever this tau is equals to 0, both the signal will be multiplied together as it is equivalent to squaring the signal, right? G square t. If tau equals to 0, it is gt multiplied with the gt, and it is equivalent to squaring the signal G square t, right? gt, right? So that time this multiplication will be giving you maximum value. And when we are varying this tau from 0 to some finite value, that time this correlation between the two signal will start decreasing, okay. This particular product is going to be decreasing. So normally here you can see this product, okay. Normally this autocorrelation function that I have defined. So here you can see this, when tau equals to 0, that time we are going to get the maximum value of this multiplication, and after that this multiplication value is going to be decreasing, okay. So tau I have taken maximum value equals to tb by 2, and normally you can either delay the signal or you can also do the advanced shifting, okay. So this signal can also be left shifted, as we have done this as a right shifted signal, and then we have multiplied. This signal can also be left shifted. So we are going to get a symmetrical curve like this if you are changing this tau, okay. This is corresponding to tau equals to 0, and then tau is slowly increasing, and here this tau value is equals to tb by 2. Similarly, you can make this value tau equals to negative values, and you will be getting this particular portion. So here you can see this time autocorrelation function that we have defined. It is actually a symmetrical curve around this particular axis, okay, about this particular axis, and its maximum value is for tau equals to 0. right? So here I just would like to mention that if you calculate the Fourier transform of this particular autocorrelation function, okay, if you calculate the Fourier transform, okay, of this psi g tau, okay, so this will be given by this particular expression. You remember this, that this tau is again a time, okay, it is again a time, it reflects the time value only, okay, it is only denoted by tau, but it means that it is a time, okay. So if you substitute for this particular formula of Fourier transforms Ig tau e to the power minus j pi 2 pi j 2 pi f tau d tau, if you use this particular formula, then you will be able to show this Fourier transform of your autocorrelation function will be equals to the energy spectral density function. Okay, you just follow this all steps, you will be able to understand easily. Some manipulation into the formula I have just done. So here you can see it is e to the power minus j2 pi f tau, and then you can redefine psi and g tau, okay, definition. So this how g tau function, psi g tau function is actually minus infinity to infinity g t plus tau d tau dt, and then with respect to d tau, we are actually doing this integration, right? So I'm just substituting for this particular expression, right? This expression I have substituted for psi g tau, and then we have to just do a I have done the rearrangement of this particular terms, okay. So I have taken out this gt outside this integration, and I have taken this particular function inside this particular integration, okay. So it is now g tau plus t, okay, and e to the power minus j2 pi f tau d tau, and then you can write the Fourier transform for this particular expression, right? So if you write this Fourier transform, you will be able to get this as a gf, okay, this Fourier transform for g, okay, that will be equals to gf. And again here you can see this particular function gt. So this is going to be give you another Fourier transform equals to g to g minus f, okay. And then obviously you will be able to show that this Fourier transform of this autocorrelation function is going to be giving you mod of gf whole square, right? So this value is actually giving you mod of gf whole square, and it means that this autocorrelation functions, if you have the autocorrelation function, if you perform the Fourier transform, then it is going to give you energy spectral density function, okay. In a similar fashion, if we are having a real power signal, okay, if we have any real power signal, again you can calculate the autocorrelation function by following this particular formula, okay. Autocorrelation function for a power signal will be limit t tends to infinity 1 upon t minus infinity to infinity, then gtt, then gt t plus tau dt, okay. So this way you have to calculate the autocorrelation function of any power signal. So you see these differences, okay. Here we don't have any limit, okay. Here we have not put it any limit, and here we are actually putting this limit over 1 upon t tending to infinity, okay. And you please make a little bit change into this particular expression, because I have just wrote minus infinity to infinity. It should be actually minus t by 2 to plus t by 2, okay. So just make this correction. It is minus t by 2 to plus t by 2. So this way you can define this autocorrelation function for the real power signal. Okay. So this way we have to define the autocorrelation function. And again, if you calculate the Fourier transform of this autocorrelation function, it is going to give you the power spectral density function. So basically in this slide, I would like to mention about this property that if we are having any autocorrelation function, if you calculate the power, if you calculate the Fourier transform, then it will be for energy signal, it is going to give you the ESD, energy spectral density function. And if it is a power signal, that time this autocorrelation function, if you calculate the Fourier transform, it will be going to give you the power spectral density function. So here you can see this graph, okay. Here we have this particular autocorrelation function for this particular given waveform, okay. Because it is a triangular waveform, if you calculate the Fourier transform of this particular function, you are going to get this type of sinc function, okay. So that you can easily show. So you will be going to get this type of sinc function. Similarly, as I defined for the this particular deterministic signal time autocorrelation function, we can also have a random processes. Okay, if we suppose we are having any random process, okay, if it is defined by capital XT, that time we are going to get the sample functions. Okay, so we are going to get the number of sample functions within the random process. So that time, if you wish to calculate the time autocorrelation of a random process, because as I said number of times, when we discuss about the noise in the communication system, okay, that time noise will be considered to be a random process. And then normally we are talking about their calculation for power spectral density function will be a little bit different as in the case of deterministic signals. So normally, if you wish to calculate the time autocorrelation function, then first we have to calculate the time autocorrelation function for a particular sample function. So let us say this is our particular sample function of this random process. Okay, let us say this is one of the particular function. Okay, so if this is our one of the sample function of a random process, and that time if you wish to calculate the autocorrelation function, then first we have to choose these two time values, T1 and T2. Okay, so this value of this particular sample function we have to determine at x equals to T1 and at x equals to T2. First we have to calculate what will be the values, right? So once you will be calculating these values, okay, if let us say this value is x1 and this value is denoted by x2. Okay, so first we have to calculate this values of x1 and x2 for a particular random function, okay, random particular sample function. And then the similar way for all other sample function, we have to calculate these values. So let us say we have considered total 4 sample function over here in this particular example. So at t equals to T1 and t equals to T2, we have to calculate what will be the values of random functions xt. Okay, so first we have to calculate this value, we have to calculate this value. Okay, first we have to calculate this value and this value, then we have to multiply it together, then we have to calculate this value and this value, then again we have to multiply it together, again we have to calculate this value and this value, we have to calculate the product, then again we have to calculate this value, and then we have to multiply it together, right? Okay, after calculating this product, all this product has to be averaged out. Okay, we have to calculate the average over this sample function. Okay, over all this sample function. That means we have to calculate the ensemble average, right? We have to calculate the ensemble average. This particular bar reflects you. We have to calculate the ensemble average, right? So in this time autocorrelation function, basically for the random process, what we have to perform, you remember, we have to first calculate these values of T1 and T2, values of the sample function at T1 and T2 for all the sample functions. We have to multiply these two values together, and then we have to calculate the average over this all ensemble, right? So this is what this average means, right? Normally, to calculate this or time autocorrelation function Rx T1 T2, we need to know this particular probability density function. Okay, so we are actually having this second order probability joint probability density function. So this is our joint probability density function f x1 x2. So what does it mean by f x1 x2 x1 comma x2 t1 comma t2? What does it mean? So it is the joint probability that this particular random process x1 is going to take this value t1, which is less than equals to x1. At the same time, x at t2 will be less than or equals to x2. So this is the probability. Okay, this is the probability that joint probability that this random process is going to take these values, right? And then we have to perform this integration over minus infinity to infinity, and then we have to calculate this random process. So this is how we actually calculate the time autocorrelation function of a random process normally. Okay, and here you can see that what it actually tells you. If you calculate the random process, I have taken this two different random process. Okay, for example, here I have taken the random process xt, and here I have taken another random process yt. So normally, as I said, that normally this autocorrelation function will give you or actually it measures the rapidity in the signal. Okay, how rapidly a signal varies that can be measured by this particular mathematical tool, which is known as the autocorrelation function, right? So here you can see that if you see this autocorrelation values, okay, because here you can see this random process xt as compared to yt, if you see this value have less fluctuations, okay, it is less random or less fluctuation with respect to this yt, because here you can see that this yt is having more fluctuations as compared to this, and therefore this particular signal is having more rapidity, okay, it is having more randomness into it, right? But here xt is comparatively having less randomness, and therefore here you can see, if you see the autocorrelation function of this xt, okay, r x tau, okay, here you can see that this autocorrelation function will have more spread, okay, as compared to this particular autocorrelation of this particular random process yt. So this way you will be able to get this random autocorrelation function of this rapidly varying signal. So whenever if you see this autocorrelation function which is very narrow, okay, it reflects that the signal is highly random, okay, it is rapidly varying in time, right? Whenever it is having more spread, okay, if it is having more spread in that time, normally the signal will having less rapidity. So this way we can actually calculate the time autocorrelation function for a random process. So overall, the takeaway from this slide is that if we have any time autocorrelation function for a random process, that time we have to average out this all values for all the ensemble, okay. And moreover, if we have this autocorrelation function of any random process, that time we have to know that if you calculate the Fourier transform, again this random process is going to give you the power spectral density function. You remember that normally any random process, specifically noise process, is considered to be a power signal, okay, it is not considered as an energy signal, because normally we consider that the noise is available for all the time, so it is varying from minus infinity to infinity, and therefore it can contain infinite energies, okay. Normally it is having a power signal, and therefore we calculate the autocorrelation function, and if we calculate the Fourier transform of this autocorrelation function, you will be going to get the power spectral density function. So again, I have the same question. If suppose we are having any signal or any random process xt, if this particular function is having its Fourier transform, which is defined by xf, if it is passed through a filter hf, then the output random process is going to be yt, and its Fourier transform is defined as yf. In that case, if we know the power spectral density function at the input side, what will be the power spectral density of this random process yt, okay. So again, we have to follow the similar strategy in the way we have calculated the energy spectral density function of the output process. If yf will be equals to xf multiplied with the hf, and if you calculate the mode, this is going to be giving you this as a power spectral density function, right? So this is going to be give you power spectral density function. So here you will be able to show that the output power spectral density will be equals to input power spectral density, okay, multiplied with the mod of hf square. So I will be stopped here, okay, today in this particular lecture. We will be discussing more about the noise calculation in the next video. So if you have any query, let me know with your comments. And thank you for watching this video, and stay connected with the channel for more updates. Thank you.